will discuss about this different kind of designing by the CMOS, and also we talk about the transmission line later, right? So we'll continue about the CMOS. Today we will try to design some memory cell like SR flip-flop, VLATch, JK flip-flop by using this CMOS cell. Though we didn't cover this memory cell, so we will discuss a little bit about how this circuit look like and how we'll get the truth table for those SR latch or JK flip-flop. So let's start with the CMOS SR latch using the NOR gate. This is CMOS SR. Oh, I'm sorry. You have to walk out because not so much is today. So at first we have to design this SR latch using the NOR gate. Let me design. So we have two inputs S and R. So this is a NOR gate. This is another NOR gate. I have two input S and R. And here we'll get an output Q and Q bar. Then we have to take our feedback path from Q and it will give you to the S latch. And from Q bar, so this is known as SR latch. This circuit is known as SR latch by using the NOR gate. Here we can see this is the NOR gate. So the last memory. So if we go for the truth table, so we have S and R, and at the output we have a complementary output Q and Q bar. As we have two inputs, so we have four combinations 0, 0, 0, 1, 1, 0, 1, 1. So out of this four combination, when both the inputs are 0, at that time we call it a memory cell, the hold circuit. That means at that time it will hold the previous data. It is hold the previous data. So when we have 0 and 1 input, so for example we start with 1 and 0. So when we have a 0, this one, S equals to 0 and R equals to 1. So what do we know? If those both of them are NOR gate, right? When they are NOR gate, in a NOR gate, when any input is high, the output will be low. So NOR gate, opposite of OR. So when any input is high at the NOR gate, output is low. So here, out of these two, here the input is high. For those case, output is low. And this output is given in a feedback part to this part. So when both input is low, output will be high. And as you mentioned that, they are complementary each other, Q and Q bar. So you can see 0 and 1. So what does it mean? Whenever we put in the SR latch, when the S input is 0, it is actually resetting. Whatever the memory cell having, it will reset to 0. So it is reset. Whenever we have now 1 and 0, so if we change the color, so when S equals to 1, this one, and R equals to 0. So the same way, so when any input is high for the NOR gate, the output will be 0. And when output is 0, this output is going to be here 0, and this 0, 0 will become 1. So that means it will, when S equals to 1, it will set. It will set. When r equals to 1, it will reset. When s equals to 1, it will set. And when both input are 0, it will remain same. It will remain same. And when both input is high, when the both input is high now, look at here. If you have both input is high, so when the both input is high, the output of the XOR will be 0, right? But we cannot have both 0 because they are complement each other. So this is why this condition is known as invalid for SR latch. So this is all about the SR latch, okay, NOR gate. Now we'll try to design this SR latch for the memory cell by using the CMOS circuit. So here we can see we have a relation, this one, Q bar and R, as this is a NOR gate, so it's just an OR operation, right? In a NOR gate, what we have? This is simply a OR operation. Because in a CMOS, we'll get the NOR inverting, so it's an OR operation. And as this is an OR operation, for CMOS, we have PMOS as well as NMOS. A pull-up resistor network and pull-down network. So this PMOS will be what? It will be in series. So PMOS in series, and NMOS will be in. Okay. So we have to design these things. Can I design here? I design here. So the PMOS, the pull-up network, this pull-up network to VDD. Then we have pull-down network to the ground, the NMOS. This is PMOS, this is NMOS. They will be in series. So we can see the series are this one. This one is which one? Q bar, right? This is Q bar and R, and this is S and Q. So we can write down, we can draw here. Let me draw here. So we already have this one. So we can write down this is NOR operation. This OR. So PMOS in series and MOS in parallel. So these are connected in series, PMOS. So two input PMOS. Now these two input will be connected in parallel. So we have two NOR gate, so I have to design two NOR gate. So this one for this NOR gate. This NOR gate. Here we have what the input? R and Q bar. So we have R, so this two is R, and this one is Q bar. But the Q bar we'll get from where? From here. So you have to design the second NOR gate. So here we have S and Q. So if we draw this S and Q, calculate the output. So what is the output here? This is the output. So for the SR latch, for the R latch, what is my output? Output is my Q. So we have that Q output here. And here, for this one, we have output Q bar. So this Q bar will be connected here. And this Q will be connected . So here we have two NOR gates. We have to design each NOR gate individually by CMOS. And this is a NOR operation, that means OR operations, it will be inverted with a CMOS circuit. So PMOS will be in series and NMOS in parallel. At first we designed this one where the input is R and Q bar. So we have R, the PMOS in series, R and Q bar, then NMOS in parallel, R and Q bar. So this Q bar is coming from the output of this second NOR gate. So output of second NOR gate is this one. Look at this one. So here we connected to Q bar, we connected to Q bar. And this one is the second NOR gate. Here the input is S and Q, S and Q. So the first, the PMOS is in series, PMOS in series, we have a bubble here. So this is a PMOS. Then NMOS in parallel, NMOS in parallel. So these two are S input, and these two are Q. So here the input is Q bar, right? Sorry, Q. So the Q is output from here. So we are giving the output through here. So this is the CMOS SL latch using the NOR gate. Okay, can you see? Is it okay? Yes. Similar way, we can design a CMOS SL latch using the NAND gate also, right? If you want to design it using the NAND gate, what will happen? In the NAND gate, everything is same. So the truth table will be the different. If I want to design with the NAND gate, so here it will be opposite one. When 0, 0, it will become invalid. And when 1, 1, it will become hold or memory. When S equals to 0, it will set. When S equals to 0, it will set. And when R equals to 0, it will reset. That means when S equals to 0, K equals to 1. When S equals to 1, K equals to 0. So as you want to use the NAND gate with the NAND gate, so NAND operations means AND operations. The NAND, we will do the AND operations. So AND operations means APP. So AND means the PMOS will be in parallel and NMOS will be in series. So let's design. The PMOS will be in parallel and the NMOS will be in series. So the PMOS in parallel, we have in the PMOS we have S and Q. S and Q bar, right? We have S and Q bar. example, otherwise you get confused. Okay. So S and R latch, S equals to Q and R equals to. So here it is Q bar. So Q will go here, Q bar will go here, and Q will come here. So S and Q bar, we have to have an S and Q bar. So they will be connected in parallel. The PMOS, and the NMOS will be connected in series. So this is S. That will get this one from other part, we'll see. And if I draw this for this one, R and Q, so there will be another, so VDD will be common, so VDD. Then we connected in series. This is R. So we have S, we have R, okay? So another input is Q and Q bar. So if I draw with other color, it will be good. So here, this is the output. Is given here. So from S, we have a Q output. So this is Q. If I take this one, so from here, we're getting Q, and this Q is given to here and here. So R and Q, R and Q. And here, output of this NAND gate is Q bar. Q bar given is here. From here, we have Q bar and Q bar here. With S, we have Q bar. So this is how, by using the CMOS, we can design SL latch. And when we design the SL latch with NAND gate, this one is the circuit. Few of you come later, please keep sign on, and pass it. Okay. Then we will try to design the CMOS D latch. CMOS data latch. So D latch is also, you can design with the SL latch first. So you already know how the SL latch is like. In the D latch, we have one input for data, another input for enable. So the block diagram is something like that. So this is D latch. We have data input, D, and then we have an enable input here. And the output, we have two complementary output, Q and Q bar. So the truth table is something like that, enable input and D, then Q and Q bar. When enable input is 0, then data will be 0. That means it will hold the previous memory or previous stage. And when the enable input is 1, then if data is 0, then Q will be 0. And if data was 1, Q is just 1, then the Q bar will be just the complementary. So we can set, so when data equals to 0, that means Q equals to 0, then it is known as set. And when data equals to 1, it will be, when data equals to 0, it is reset to 0. And when data equals to 1, it is set. So this is the truth table. And if I want to draw the circuit of D latch first inside this block with SL latch, so we already have our SL latch circuit with the NOR gate. This is the SL latch circuit. Here we have S input, we have Q input. With the S input we have Q bar, and with the Q input, R, we have the Q. Then we have the feedback. This one is the normal SL latch, right? Now here in the D latch, to design a D latch with SL latch, we have to have an AND gate here. We will have an AND gate here. And in the AND gate, we will have two inputs. It's a 2-input AND gate. One is the enable input, another is the data input. So this data input will be like this. So data will be driven or directly to the S input, and it will be given to the R through a NOR gate. And this is the enable input. So of course, whenever enable input is 0, so when enable is 0, so output will be 0. So when SR is 0, 0, it is a memory cell, right? Previously said that it is hold the memory of the previous stage. And then when enable input is 1, then S equals to 1 and R equals to 0, so it will be reset. And when S equals to, set, when S equals to 0 and R equals to 1, it will be reset. So what we can see, the Q bar and Q, we can write down to implement by CMOS. So Q bar is equals to what? Q bar is equals to D in times enable plus Q. Data input dot enable input plus Q, the whole bar. Right? The Q output. This is Q bar, right? This is the output. What is the output here? Output of AND gate. Output of AND gate what? D in. So D in times enable plus Q whole bar. Right? Similarly, the Q is equals to D in bar dot enable plus Q bar. So now we can easily implement this one. We have a AND operation, we have an OR operations. So we already know what to do for AND operation and what to do for OR operation. If I do, so APP, so AND operation with parallel in PMOS, right? So at first AND operation, we do the AND operation. So PMOS will be in parallel, AND operation. So these two will be in parallel, D in and enable input. So this is D in, this is PMOS. PMOS, say this is D in, this is enable input. Then this one connect as OR with Q. So it will be OR. Let me series with this one. And these two will become series. With parallel with this Q bar. this is my pull-up network. So we have to connect with VDD. PMOS. You have to make sure that PMOS. This is my pull-up network, and this is my pull-down network. These are in series NMOS connected to the ground. So this D in parallel with enable input. These two will become now in series. This parallel connection connected in parallel series with this one output, which is Q bar. So this is my Q bar, and these two will be connected in parallel. So output will be Q. So this is output of. So this is the first time logic. Then you have to draw the second one. For Q bar, we can have this one here. The same VDD, we can apply the same VDD. So here we have D in, bar and enable. D in bar and enable. PMOS. Here D in, then enable. It will be connected in series with Q. So this is Q. Then this will become in series. And then it will be connected in parallel. Then connected to the ground. This one is also Q. This is D in, so this is Q bar here. This is Q bar, and now this will be the Q. So here we have Q bar, we have Q, and so now we can connect this one to this one and this one, and here we connect. It will be enable and D. So this is how we can design a PMOS device. Okay. So you have to be very careful about this PMOS and NMOS. So these are the PMOS. You can also use the arrow, inward and outward arrow, or you can use the bubble. So just use the bubble, it will be more convenient to remember. Otherwise, sometimes you can make interchangeable with the arrow, because in the PMOS this arrow will be here, in the NMOS arrow will be here. So it is more complicated to remember. You just use the bubble. So both are the PMOS. So this is a PMOS pull-out network. Again, and this is a pull-down network, the NMOS. And we take the output. Output is always the inverter. So this is how we can design these things. Then we will try to design the CMOS SR flip-flop using the NOR gate. So we have done the SR latch and D latch. Now we will focus on the SR flip-flop, the memory. CMOS SR flip-flop using the NOR gate. So let me design the first. So this is almost similar. At first we have our SR latch, similar SR latch. So S and R. So it will be Q bar and Q. We will take each feedback path here and give it to this one. And then here we have our AND gate, input AND gate. Here, previously in the D latch, we have our enable input, right? Here we have our on signal. This is the difference between the latch and the flip-flop. In the flip-flop, we have a clock signal. So this is the on signal. Again, this is our SR. So we can denote it with an S star and R star. So give our SR input here to the input AND gate, and other two inputs are the clock input. Then it will give it to the SR latch. Okay. So in the SR flip-flop, so we have clock input, then we have SR input, and then we have Q and Q bar. So of course, when clock is 0, so it will not work. The SR will be visible, and it will like a memory, right? Or hold. And of course, when the clock input are there, so SR input will have 4 options: 0, 0, 0, 1, 1, 0, 1, 1. So it will be the same. When 0, 0, it will be memory or hold. When it will be S equals to 0, it will be reset. When S equals to 1 or R equals to 0, it will be set, and this one is invalid. It is similar. But it will be a little bit complicated with the circuit, because now we have the equation for S, for Q and Q bar is something like that. For Q bar we have S star. S star means S into S clock, S into clock plus Q whole bar, and for Q is R into clock plus Q bar. So this will be the, so instead of enable input, we have just now the clock input. Okay? So we can design the same way. Just now we saw the D latch. But here it is the clock input. Then we'll see the last one of the memory. It is a CMOS JK flip-flop. The difference between this JK flip-flop and the SR flip-flop is that we have a feedback path from the output to the input. From the output to the input, and in that case, we'll see, so far we see whenever we have 1, 1, we have an invalid output. If it is a or NOR gate, and if it is a NAND gate, it's just opposite. But in case of JK flip-flop, it will actually give you a toggle, right? Toggle. So we are not talking about the JK flip-flop, we are talking about the JK flip-flop. Let's see how it will work in the JK flip-flop. So in the JK flip-flop, everything is same, SR clock. Now we have another clock. It will be 3 input AND gate. We'll get another input from here. So Q bar and Q. This is the JK flip-flop circuit. This is the difference. In the JK flip-flop, we have a feedback path from the output to input, from output to input. Okay? So, of course, obviously, when clock is 0, what will happen? When clock is 0, JK flip-flop will not, because the output of the AND gate, any input of the AND gate is 0, output will be 0. So, it is an SR latch, it will be just as a memory output. Memory output. clock equals to 1, again when 0, 0 is set, it will be memory output. When 0, 1, it will be saying S equals to 0 instead of S. So SLH, still is an SLH, so it will be reset to 0. And what is 1, 0? It will be set to 1, 0. So now, what will happen if you look at here, when the last option is, the last one, last operation we can say, this is Q bar is equals to what? Q bar equals to 0. Q bar equals to 0 and Q equals to 1. Okay, Q bar equals to 0, Q equals to 1. So that means Q equals to 1, Q bar equals to 0, right? So when both input is 1, what is happening here? When both input is 1 of the JK flip-flop, sorry, it is supposed to be JK now. When both input is 1, so here we have 1, in the clock we have 1, and now the Q bar is what? 0. Q bar is 0. So when any input of the AND gate is 0, output will be 0. Here, K equals to 1, clock equals to 1, Q equals to 1. All input are 1. And we already know when any input of the NOR gate is 1, logic high, output is logic 0. So it will get toggled. Previously it was 1, now it becomes 0. And this 0 will come to here, and this 0, 0 will become 1. So this is the main difference between the SF flip-flop and the JK flip-flop. The SF flip-flop don't have this toggle output. It has invalid output. In case of a JK flip-flop, we'll get a toggle. So now output will become 0 and 1. So it will keep toggling. 0, 1, 1, 0, 0, 1, 1, 0. So this is the JK flip-flop by using the NOR gate. Now we have to design with the CMOS. So what is the CMOS operation? So CMOS will be PMOS APP, right? AND operation, PMOS will be parallel. OR operation, PMOS will be series, like this. Okay. So what you need to find out? You have to find out the Q and Q bar, right? In the Q bar, what we have? In the Q bar, now we have 3 input, J, clock, and Q bar. J dot clock dot Q bar. Sorry, for the Q bar, J Q bar plus Q whole bar. And for the Q, it is K clock Q, K dot clock dot Q plus Q. Right? Here, you can see here, this is my output. We are talking about Q bar. Q bar is what? This input. So what is this input? S bar. S bar is nothing but output of 3 input of NAND gate. The clock dot J dot Q bar. Clock dot J dot Q bar. And this is AND operation with what? With Q. So it's just a 3 inputs and gates. So this is the AND operation. So in the AND operation, PMOS will be in parallel. We have 3 transistors. We have a 3 transistor here. In the VDD. Q bar, this is J, this is clock. So J, clock, Q bar, plus Q, and that is OR. that is odd. Series. Then these two will become in series. And these two will become parallel. So this is Q bar again. So these two are Q bar. And this is J. And this is clock. This is Q. This one also Q. So we have PMOS, 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 PMOS connected in parallel, then in series, connected in series, then parallel. This is NMOS, this is PMOS, and we'll get our output from here. It will be the Q bar. It is Q bar. Then if I design for the Q, KL, so again, they will be in parallel. So we have three PMOS, 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 K and Q. So okay. Just for our easy to draw, I just want to draw here like this. Okay. So it's a clock is K is Q. Then we have in series with Q bar, Q bar, PMOS. Then in series, this one connected in parallel to the ground, this one for VCC, this one block, this one for K, this one for Q. And this is for Q bar, this one for Q bar. So Q bar is coming from here. We connect the Q bar here. And this Q is coming from here. The output of here is Q. It will connect. So this is how we can design all the flip-flops by using this CMOS circuit. Okay. So we already saw how to design any NAND gate or NOR gate using the CMOS circuit. We can also design any flip-flops, any latch or memory cell using the CMOS circuit. And in our last class we also discussed about the transmission gate, right? The transmission gate is including in one PMOS and one NMOS. We can also solve it. Before, as I mentioned today, I need to stop early. Just before stopping, I just want to talk a little bit about one more thing that is known as pass transistor logic. That is known as pass transistor logic. It has some advantages over CMOS logic circuit. I'll talk about those advantages today and disadvantages. This is known as pass transistor logic. In pass transistor logic MOSFET are used as a switch. So we already know the PMOS and NMOS. And this PMOS and NMOS actually act like a switch, right? So whenever the MOS transistors are in odd condition, then it passes the logic 0 or logic, any logic. So for example, this is NMOS, and this is our PMOS, right? You know, so this is my input side, for example, and this is my output side. This is input side. This is my output side. So this is known as PMOS, sorry, NMOS, and this one is PMOS with a bubble here. So whenever they are on, the transistors are on, then we can connect from input to output. Or we can say that we can pass the logic from input to output. And when they are open or they are not connected or off, we cannot pass our logic information from input to output. So how we can turn on this the transistor or the MOSFET? So if I draw the NMOS here, this is my source terminal, this is my gate terminal, this is my drain terminal, right? So this is positive source connecting ground, VGS. So you already know when VGS is greater than the threshold voltage VT, the transistor will on. And when the transistor will on, we can get the connection, the transistor will on, we'll get the output. So we pass the logic. And when VGS is less than this threshold voltage, it will become off. This is for NMOS. In case of PMOS, it is opposite. In case of PMOS, the source is connected to VCC, the drain is connected to the ground, the gate is at negative terminal. Then VSG should be greater than VT, right? VSG should be greater than, or we can say that VGS is less than VT, then it will turn on. If VGS is greater than VT, it will be turned off. So here in pass transistor logic, we will use this PMOS and NMOS, any one. We will not use both. In case of CMOS, what is the advantage of this pass transistor logic over the CMOS? In case of CMOS, we require a pair of NMOS and PMOS. A pair of NMOS and PMOS. So, but here, in case of here, we require a less number of logic circuit. For example, we already designed, whenever we try to design a 2-input NOR gate or 2-input NAND gate, we require 2 PMOS and 2 NMOS, total 4 transistors. If we want to design an XOR circuit or XNOR circuit, we require 8 transistors, 4 PMOS and 4 NMOS. But we will see that in case of pass transistor logic, we require less number of transistors. This is one of the advantages. Another advantage of this circuit, of this pass transistor logic, is it is basically a ratioless. What does it mean? It means in case of CMOS, we have a PMOS as well as a CMOS. A PMOS, in case of PMOS, what we have? In case of PMOS, the majority is whole, right? The main majority carriers is whole. In case of PMOS, holes are my majority carriers. We have a P channel. In case of NMOS, we have an N channel, electrons is the majority carrier. And we are using in CMOS both PMOS and CMOS. But we already know the mobility of electrons and the mobility of holes are not same. The mobility of electrons, the mu, is higher in case of electron than the mobility of holes. So when we have turned on the transistor for PMOS and NMOS, there is a value called on resistance. Due to that mobility difference, this on resistance will not be the same for both PMOS and NMOS case. That means we need to scale up during the design, during the fabrication, the device fabrication, we need to scale up the PMOS so that we can get the same resistance value at on condition. So a scale up is necessary. Okay, but in case of pass logic, we are using only one type of MOSFET, either NMOS or PMOS, so it is known as ratioless. So that's why the pass logic circuit is a ratioless, and this is the one advantage. And the second advantage is it requires less number of transistors. Okay. These are the two advantages. But there is some limitation of the disadvantages. The first disadvantage of this pass logic circuit is known as threshold voltage drop. The first limitation is the threshold voltage drop. What does it mean? So PMOS and NMOS will not act as a perfect switch, and while passing the logic, there will be some voltage drop across the two transistors. We are using this PMOS and NMOS as a switching, right? Here, in case of digital electronics, we are using this transistor as a switching. But they will not a perfectly mechanical switch. There will be some, when there will be turn on, there will be some voltage drop because there is an on resistance, so there will be some voltage drop. So, if we have this voltage drop, for example, and we also know that NMOS is good to pass logic 0 and weak to pass logic 1. On the other hand, PMOS is good to pass logic high, but weak to pass logic 0. Okay. So I have these things all here. Now in the pass transistor logic, we are using only the NMOS, right? So if we have the NMOS in such a way, for example, so this is the control input, 5 volt. This is my input, 5 volt. 5 volt. So this is the gate terminal. This is the control gate terminal, control gate terminal, control gate terminal. In the drain terminal, we are giving our input. Okay, we are giving our input, and we just consider the threshold voltage Vt is 1 volt. So here we are giving logic high, 5 volt to each input, 5 volt to each input, and the control voltage at the gate terminal also given 5 volt. So what will happen? If we connect this way, that means connected in parallel way, right? We are giving parallelly all the input. So what will happen? A one threshold voltage drop will across each transistor for logic 1. There will be a one threshold voltage drop for each transistor for passing logic 1. So whenever the output of this pass transistor drive the gate terminal of the other transistor, then there will be a threshold voltage drop for each transistor. So this one, look at here, this is the output of the first transistor. So this output is connected to what? Gate terminal for the second transistor. Then again, this is the output of the second transistor. It is connected to the third gate terminal of the third transistor. So as I mentioned that, whenever the output, this is the output of the first terminal drive the gate of the other transistor, there will be a threshold voltage drop. Okay. How this one? So for example, for the first transistor, look at here, this is the first transistor, this is the second, this is the third. For the first transistor, what we have, we consider that threshold voltage is 1 volt, right? And we have given input voltage 5 volt, and here we have 5 volt to the gate terminal. So this is the source terminal, right? So Vs, so we can write down this Vs is equals to Vg minus Vt. We already know, right? The source terminal, it should be maintained this one, Vg minus Vt. So what is my gate terminal? Gate voltage is 5 volt, and my threshold voltage is 1 volt. So 5 minus 1 is equals to 4 volt. So here we have a 4 volt here. Now for the second transistor, the gate voltage is now 4 volt. So here Vs equals to now Vg minus Vt is equals to 4 minus 1 is 3 volt. Now here at this output we have 3 volt. So this is the control gate voltage for the third transistor. So now here Vs is equals to 3 minus 1, 2 volt. So for passing logic 1, each transistor have a 1 threshold voltage drop. So if you keep connecting it, at some point we can see maybe it will not recognize this logic high because it will go less than the threshold voltage. right? So it is the main thing that we mentioned, that the NMOS is not strong enough to pass logic high. Why? So if you can remember the previous, we already talked about these things. For example, look at here. So here 5 volt gate control voltage, and our D is the 5 volt at the drain terminal, and the source voltage is now here. So we already know VGS is equal to VG minus VS. At the very beginning, source is 0. We have 5 minus 0, 5 volt, right? At the very beginning. So now, as soon as the voltage source, so when the voltage source will keep increasing here, when VGS is greater than VT, so at that terminal, the voltage volt will keep increasing at the source terminal. When they will reach to equal to some voltage like 4 volt, so what will happen? The difference will be 1 volt. Our threshold voltage is 1 volt. So when it will be more than 1 volt, that means this terminal will become not 1 threshold voltage. So it cannot pass the signal. That's why we have to maintain this one. Similar thing is happening here. So if we keep increasing, if connecting parallelly, this NMOS will reach to the threshold voltage. So this is the drawback or the disadvantage of this one is the threshold voltage drop. So what does it mean? We cannot connect in the first transistor in the parallel connection. We have to connect in the series connection. So that means if we connect here, instead of parallel connection, if we connect these things in series, now if you give the 5 volt here in the drain terminal, this is the source terminal, this is the gate terminal. For example, here we have control gate voltage 5 volt, and threshold voltage is again still the 1 volt. So now here we can see 5 minus 1, 4 volt every time. Still here the threshold voltage is Vs equals to 4 volt. Here Vs equals to 4 volt. So then it can overcome this issue. Okay? So in case of parallel, we cannot have a voltage drop issues for the pass logic transistor. So we can connect this in the series connection. So output voltage will be different in the, but of course here we just consider the control voltage is fixed. But if the control voltage is changed, then it will be different. For example, if now control voltage is, for example, this one 4 volt, then what will happen? So here we can see here it is 4 volt, but this one 4 minus 1, 3 volt. But the source terminal will be at lower potential. So it will be 3 volt. So now when it is a 3 volt, now if you come here, so it will be 3 volt, but now again it is 5 minus 1 equals to 4 volt, but we have a 3 volt. The source terminal should be always in the lower potential. It will be 3 volt. So something like that. Another limitation is this pass transistor logic is when we connect this multiple transistor in series, then it will reduce the speed. It will reduce the speed because whenever they are turned on, we can consider this transistor as turn on resistor, then turn on resistor, then on resistor, right? This is an on resistor of the L channel. When there is a channel, there is a resistance. This is an on resistance. At every transistor at the output terminal, there will be some parasitic capacitance. So it will become an RC circuit. So this is just a 3 transistor. If you just have more than that, there will be an RC circuit. And when there is an RC circuit, we already know it's a long chain. it's a chain reaction, so it will reduce the speed of your circuit. So these are the limitations of this fast transistor project. So I finished today. Today I have to finish a little bit early, as I mentioned at the beginning. We'll continue here in the next week. This Wednesday we'll have our next this Thursday we'll have our exam. So we'll continue on next Tuesday.
Professor, what is the fact? Question, paper fact.
So question will be, madam, the sample questions I have given from here, that will be the
How the question and how the
I will post it tonight.